Welcome to Chapter 11, Section 3 on polygons. A polygon is a simple, closed figure formed by three or more line segments that we're calling sides. So something that has one line segment is not a polygon because you can't close it. It would be open. It would just be a line segment. If I had two line segments, again, it's open. So it's not a closed figure, cannot be a polygon. I cannot close the figure until it has three sides. Three-sided figure is a triangle. Four-sided figure, quadrilateral. Five-sided, pentagon. Six, hexagon. Seven, heptagon. 8, octagon. 9, nonagon, and 10, decagon. You should have at least these memorized, 3 through 10. Triangle, quadrilateral, pentagon, hexagon, heptagon, octagon, nonagon, and decagon. So the instructions here say determine whether the figure is a polygon. If it is, classify it, and if not, explain why. So this first one looks like this. Okay. Is this a polygon? Well, I look at it, and it's a closed figure. It's not open. Okay. They're intersecting at the endpoints here, and they all have line segments. There's no curves in it. So I would say, yes, it is a polygon, and classify it by its number of sides. I would say this is a hexagon because it has 1, 2, 3, 4, 5, 6 sides. So if you go back to the definition of a polygon, number 1, it has to be closed. Okay? Number 2, it says that they have to be connected with line segments. So there can't be any curves. And number 3, the sides cannot overlap. So we had things that were open, we can't have something with a curve, and we can't have something that overlaps. So again, this one, it checks off all those boxes. There's no curves, it's closed, and there's no overlaps. So again, I would say yes, it's a polygon, and when I classify it, I would say it's a hexagon because it does have 6 sides. The next one gives me a picture that looks like this. Now, I notice here I have one side, okay, but I do have a curve. So even though it's a closed figure, this is not a polygon because it's curved. So I cannot classify it by its number of sides. It breaks the definition of the polygon, a simple closed figure with line segments, in that it's curved. So you can always check off these 3 things. It is closed and there are no overlaps, but the curves part doesn't work, therefore it's not a polygon. Okay, a diagonal is a line segment that joins 2 non-consecutive vertices in a polygon. So consecutive would mean one after another. So non-consecutive means you would skip. So draw the diagonals for these shapes. We're just going to draw one for each. Not one for each. Let's say diagonals from one vertex. So if I pick this vertex, I can't draw any diagonals here because if I were to connect any of the vertices, they're consecutive. They come one after another. And I would just be tracing over the sides. So that doesn't work. If I drew one here, that's not a diagonal because it doesn't go to another vertex. So this one would have no diagonals. Okay, the next one, let's say I pick this vertex. Okay, if I draw this line, it's actually a side. So I can draw one diagonal. Because if I draw any other ones, it would just be a side, one diagonal from that vertex. If I pick this vertex, I can draw two diagonals. If I pick this vertex, I can draw three diagonals. Okay, if you look here, now it's all split into triangles. I have one triangle in this one, two in this one, three in this one, and four in this one. So let's take some notes here. In this first figure, it's a triangle. The number of sides is 3. The number of triangles is 1. In the second figure, this is a quadrilateral. It has 4 sides, and it has 2 triangles. The next one has 5 sides and 3 triangles. The last one has 6 sides and 4 triangles. So you may see a pattern. To get from here to here, I subtract 2. 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 So it says, notice the number of triangles is 2 less than the number of sides. So I could write this out as n minus 2. Now, why would that be helpful? You can use this to figure out what all of the angles in any polygon adds up to. So if I know that a triangle has 180 degrees in it, and I know that I can break down any polygon into triangles, I can use this formula. The sum of the inside or interior angles is going to be n minus 2, the number of sides minus 2, times 180 degrees. That's going to give me the sum of all of the angles inside any shape. So this one says, find the sum of the measures of the interior angles of a 13gon. That means the number of sides is 13. So I'm going to plug it into my equation. N minus 2 times 180, which would give me 13 minus 2. PEMDAS tells me to do subtraction in my parentheses first. And now I'll multiply to find that in a 13gon there are 1,980 degrees. Let's try another one. The sum of the measures of the interior angles of an 18gon. That means my number of sides, my n, is 18. So I'll write out my formula, and where I see n, I'll write 18. Parentheses first. So in an 18gon, I have 2,880 degrees in the interior angles. A regular polygon is a polygon that has all sides congruent and all angles congruent, meaning all sides are equal and all angles are equal. So if I scroll back up here, you may have looked at the 4-sided quadrilateral and gone, don't we just call that a square? Well, no, there's other things that have 4 sides. We have a rhombus, we have a trapezoid, There's a rectangle. There's lots of different things that have 4 sides. But you think of square most often because that would be the regular polygon. It's got 4 congruent sides and 4 congruent angles. If we're talking about a triangle, yesterday or in 11.2, when we were talking about triangles, we said an equilateral triangle is one that has all sides congruent. So an equilateral triangle would be that regular polygon. They're things that just seem normal. They're often more common. So they have all congruent sides and all congruent angles. Let's try another problem. What is the measure of an interior angle of one of the pentagonal panels in a soccer ball? Well, first thing I notice, pentagonal. Pentagonal means my number of sides is 5. All of the shapes on the soccer ball are regular. They're not all different sizes. That pattern repeats all the way around. So I'm looking for a regular pentagon in that all the sides and all the angles are going to be equal. I also notice that it doesn't say the sum of the interior angles. It wants one interior angle. Well, my equation for the sum is n minus 2 times 180. So I can find the sum of them first. I'm going to plug in 5. So now I'm just going to go through and simplify. Like I said, I'm going to do PEMDAS first. 5 minus 2 multiply by 180. And now I have the sum of the interior angles. But I want to know just one. Well, if they're regular, if they're all equal, and I know there's 5 of them, then all I have to do with the 540 is divide it by 5. And that'll give me one individual angle. Each of the angles in a regular pentagon is going to be 108 degrees. So this one's just taking it one step further. Instead of it asking for the sum, it wants just one single one. So I have to add that extra step of dividing at the end. A repetitive pattern of polygons that fit together with no overlaps or holes is called a tessellation. The sum, so I'm going to be adding things up, of the measures of the angles where the vertices meet is 360 degrees. So if I were to draw out something like this, I could say this pattern was formed by 4 squares. Okay? This one could be 90 degrees, and this one, and this one, and this one. So when I add them up, all of those center ones, 4 times 90 is 360. If I had another pattern, something like this, I might say 45, 45, 45. All of the angles where they meet in the middle all the way around, well, there's 8 of them. 8 times 45 gives me 360 degrees. So these ones are going to ask you whether or not you can make a tessellation. So we're going to go through a couple different steps. The key here is that there are no overlaps. This one came out to be nice. There's one here, one here. There's not overlapping at all, nice and even. Same with the ones where I had 45 degrees. So if I have a pentagon, that means my n is 5. Okay, so the next one, I have an octagon. That means my n is 8. We need to figure out if this will work nicely. So we got to figure out what the measure of each interior angle for each of these is going to be first, and then see if it's nicely divisible into 360. If 360 is divisible by our interior angle, then we're going to be able to create this nice pattern. If it doesn't go in evenly, then our answer is going to be no. So let's find out what one angle of a pentagon is going to be. I'll start out by finding the sum, n minus 2 times 180. So I find that the sum is 540. We know if we want to find 1, I need to divide it by the number of sides, which in this case we said was 5. We want to know if we put a bunch of pentagons together, if it'll fit nicely in that 360 degrees. So is 360 nicely divisible by 108? That's what you're asking yourself. Can you repeat this pattern? Well, when you do 360 divided by 108, it doesn't come out very nicely. We get 3.3 repeating. That means I would have 3 1/3 pentagons. That's not going to work out. We're going to have some overlap there. It's not going to be a nice pretty pattern like we had above. So the question is, determine whether it can be a tessellation. The answer would be no. It is not evenly divisible by 108. So let's try this pattern one more time. Step 1, plug it into the sum equation. So I'm going to get 180 times, we already said octagon was 8, 8 minus 2, Step 2 is to figure out what one individual interior angle would be. So I'm going to divide that by 8. And step 3, see if we can arrange them in a nice pattern. .6 repeating. So again, it's not going to be that nice pattern. I would say no, it is not evenly divisible by 135. So both of those answers are no. If it was yes, it would come out to be a nice even number. Okay, no decimals because we would have no overlaps there. So that is the end of section